Hey everybody, welcome to PyData Amsterdam. Thank you so much for being here. Thank you to NumFOCUS, to PyData, to all the organizers. Give them another hand. Look at how beautiful this venue is. Look how much work this was. And thank you to all of you for being here. It's so wonderful to see everybody in person and to be at an in-person conference again. So today, this talk is going to be about context windows. I was already very wonderfully introduced. If you don't know me, I'm Vicki. I'm also going to put all the slides, all the links. There's a lot of content, as is usual for me in this talk. It's going to be on my website after this, hopefully soon. I already have a pull request out. So yeah, I'm a machine learning engineer at Duo Security. You might also know me from such former hits as Normcore Tech, the newsletter, NormConf, the conference about boring stuff in machine learning, and Vibrary, which is a semantic search engine based on vibes. And I also wrote a small paper about embeddings recently. Today, though, I want to talk to you about something, and also I used to tweet stuff back when Twitter was still a thing. And it turns out I got to do number one, which has turned this into a conference talk about AI. Today, though, I want to talk to you about something that's been worrying me over the past year. Now, as a machine learning engineer who's responsible for putting stuff in prod, and as an Eastern European, I'm worried and concerned and cynical about stuff almost every single day. But what I want to talk to you about, there's a bunch of stuff that worries me, right? Data drift, nulls, notebook cell execution order, don't put them in prod, unpinned dependencies, service SLA violations. The thing that I'm worried about today is the two fundamental problems in computer science. You might know them already: cache invalidation and naming things. And we're going to talk about why they're important. So this joke comes from Phil Carlton, who used to work at Netscape in the early 1990s. Netscape was a really important foundational company in the history of the internet. And they were responsible for stuff like JavaScript, cookies, SSL, so they were a foundational architecture of the internet. Why are we taking a deep dive into the history of what happened in the early 1990s? Because history is context, and context is power. And the more context that we have in any of the given work that we do, the better our work is, and the better and the stronger it becomes. To illustrate this a little bit more, I want to talk about machine learning. So that's one of the reasons why we're all here, right? So machine learning is the art of extrapolating patterns based on past data. This is from Russell and Norvig. It's a foundational text in AI, a modern approach. And what are we, if not the original machines that learn? We need to take context and train our own mental model. In other words, our own machine should be a little bit tired at all times. So to motivate this a little bit more, I want to step back even further and talk about why context can be important in a global sense. And I want to do this by talking about the two Piranesi's. The first is a book by Susanna Clarke. It's one of my favorite books that I've read in a long time. It's a fictional account of an unnamed narrator who lives in the world. We don't know where this world is. We just know that it's a big empty house. On the bottom, there's a big ocean that collides with other waters. There's millions of corridors, and then the house is open to the sea. The unnamed narrator thinks that he's always lived here, and we know this because he records everything that he writes in a notebook. So he keeps the memories, but then the tides wash them away. So he still has some of them, but really he loses most of those notebooks. He thinks that he has always lived alone in this house, and we don't really know what's happening to him. There is one other person in this house, and that is the other. And he kind of comes in and out. He's very well dressed. And it's through interacting with this other and through the notebooks that Piranesi realizes that things aren't what they seem, and what he's actually experiencing is a lot of memory loss. And with the help of some notebooks, he's able to finally figure out what happens. I won't give away too many spoilers because it's a wonderful book, and you should read it if you get the chance. But what the other does is he jokingly calls him Piranesi, this unnamed man. And this is not explained to or alluded to in the books, but what this is it's an allusion to the other Piranesi, which is Giovanni Battista Piranesi, who was an Italian or Venetian architect and engraver and artist who was born in the 1720s. His brother installed a very strong love for Roman architecture, for art, and for classical culture in him. And he went on to Rome to do a lot of sketching and engraving. And so before he did engraving, he did a lot of drawing and a lot of studying. And what happened was that he recreated the classics. He did very, very meticulous sketches of all the ancient Roman landmarks. And he created a book called Views, where he really meticulously studied them. So here's some other examples. And when he was looking at all of this ancient stuff, he was a little bit upset because a lot of it at the time was very dilapidated. It was ruined, it was run down. It was in fields or in gardens, or it was being destroyed. There was no real sense of preservation of any of this stuff. And so what he wanted to do was preserve it by means of sketching it or engraving it. He went on to become very successful as an engraver. But what happened was, because he did so much studying of the classics, he was then able to do a series of sketches of imaginary prisons. And a lot of these are used today as kind of foundational views for how you should draw worlds or build video games. And he was only able to do this because he had done so much studying of the classics, so you can kind of see the echoes of ancient Rome in all of these. But these are all completely imaginary things that he created. So by doing that, he was able to build on them. And here's some examples. And this is how it alludes back to the book of Piranesi, because Piranesi himself, the imaginary one, was trapped in what was kind of an imaginary jail. So what do these two things have to do with each other? They both relate to memory and context. In the first one, Piranesi, the imaginary one, was held captive by what he imagined was going on, and he couldn't get out of this house because he didn't have any memory. Eventually, it was his diary that led him to understand what had happened to him, and he was able to trace his way back. And the second Piranesi, because he had studied history and because he had so much context, he was able to draw on that. He was able to not only preserve that history, but also build on that and create new imaginary worlds for himself. So why are these things really important? Because right now, the stage that we are in machine learning engineering and data science and all of that is just kind of like a baby stage, right? We've only been at the practice of software engineering for the last 50 years. The precepts of information retrieval, of computer science with Allen and Vannevar Bush was in the 1940s. Ada Lovelace, who's considered the first developer programmer, was at most 100, 200 years ago. Electrical engineering was only invented 250 years ago. Math and physics are really old, right? So where we are right now in the data world is we're at like the very, very beginnings, even though it might seem like forever ago. So I put Hadoop here because we think of Hadoop as an old technology. But it's from 2006. So all of this is important to keep in context for how much has actually come before what we're doing and how much swirl there is in the current data ecosystem. So if you look at this, machine learning is 50 years old max. But the concepts have been reinvented time and time again. And if you look for them, you'll see that the patterns are there. So, sorry for the slide. I know there's a lot going on there. But if you look at it, it seems like there's an overwhelming amount of stuff. How do we navigate our way through it? How do we form our own context windows? How do we hang on to what's important? How do we take control of the flood? One way we can do that is do what Ellen Ullman did. So Ellen Ullman is a really strong developer. She worked in the 70s, 80s, and 90s at startups, at large systems. She did a lot of C, a lot of Fortran, so super hardcore developer. And she is, a really prominent writer and thinker about software systems. And in one of her books, she wrote an essay called The Dumbing Down of Programming, Some Thoughts on Programming, Knowing, and the Nature of Easy. And in this essay, what she did was she wanted to uninstall Microsoft Windows and install Linux. And this was in 1998, so you have to understand the craziness of what she was trying to do. People were lining up at midnight to buy Windows 98. Windows was, as Microsoft is today, at a very peak popularity high. 15 million installs of Windows NT alone. To get an idea of how much that is in today's world of apps that have hundreds of millions of users, only 43% of people had computers and the internet at that time. So what she wanted to do was install this operating system that this guy invented that was just a hobby. He said it won't be big and professional. But Linux was already growing in popularity at the time. In order to do all this, she had to do this series of steps. So first, she had to get CD-ROMs of Windows NT. She had various stages and different stages of upgrades, so she did that. Then she had to repartition the hard drive, which you have to insert the floppy, find the right floppies. Then she had to reformat the hard drive to include only DOS, which is the underlying software system. Then finally, she was at the point where she wiped everything, and she was essentially at bare metal with no operating system. And at that point, she got this error, no ROM basic, system halted. What does this mean? What was this error message? So it turns out the way that the software was developed was you had Windows on top, then you had DOS underneath, then you had BASIC, and then underneath all of that, if anyone's doing talk about date times, and IBM PCs, 1980 was year one, so everything was based on that. So she deleted the first two parts, and then she got to the point where the operating system was basically looking for BASIC, which it didn't have. So what she found was that she had not seen a PC with built-in BASIC in 16 years. But there was a vestigial trace of the history when she unearthed everything. This is really important because all the systems we build have these vestigial traces. We can look for them, and if we dig through the pyramid of what's really happening, we can understand the concept. Later on, she wrote, "We build our computers the way we build our cities, over time, without a plan, on top of ruins." When we build software, we might want to think about this as a form of context. So how do we build our context window? Now we come to the actual problem of the talk, which is cache invalidation. So when we have an application, any application, we have two fundamental things that we're trying to solve in it, in a web app. We have processes that are I/O bound, so we're trying to move data from one part to the other. And then we have processes that are CPU bound, so we're trying to process that data in memory. And most of the app is concerned with these two problems, particularly these days when you have cloud architectures. Moving data between two machines is really, really, really expensive. This is a problem in all applications. You can see this pattern everywhere. In fact, in a recent article about machine learning called Distilling What We Know, this is an ACM article, they talk about the bottleneck problem, which is the problem of moving computations to the GPU, so you can parallelize them. So it's talking about no longer how fast you can perform computations, but how fast you can feed data into the system. So again, I/O bound and CPU bound. It's a very common pattern. So what happens is we have to design our software to work around those systems and to work within those constraints. All of our software is always working within the constraints of time and money. And often, so Sarah Hooker has this great piece that she wrote called The Hardware Lottery about ML computing, where she said research ideas win because they're compatible with the available software and hardware that we have, and not because the idea is the best. So we're always pushed in the direction of constraints when we design our systems. Even the Jacquard loom, which happened a long time ago, is thought of as one of the first programmable machines. It was so expensive to rethread, it was typically threaded once. So this is the first example of caching. In order to prevent having to recompute and move data, what we can do is we can put it into a cache. And a cache is essentially a piece of software that operates in memory, in RAM, where we can put all of our results instead of having to hit the database constantly all the time and have it available in cache for us to retrieve from our application. So this is a really great pattern that works around the constraints of having to always be I/O bound. If we think about it in Python, since this is PyData, how do we do these lookups against caches? We have a set of key-value pairs. What is the set of key-value pairs? It's just a dictionary. So you have a key, and you look up a value. That's it. That's how a cache works. Even ChatGPT, which has architecture that's so expensive that it has to basically run for $700,000 a day. This is all the stuff it has to do, right? So when you enter something into ChatGPT, you have a query, then it has to authenticate you against the server, then it checks the cache to see if the query is there, which is how it gets that list of titles and chats on the sidebar. Then it performs the model inference, which is when it starts typing, when they did like this really clever trick to make the pointer blink so that you would know it's doing inference. Then it returns the results. Then it adds those results to cache so you have your chat history, and has to do all of this in milliseconds. So this is all really expensive, $700,000 a day. Expensive for millions and millions of users. But it also has this chat cache. So this is great. This is a fantastic pattern. It helps make our applications performant. When we find stuff in the cache, that's a cache hit, and we can get it directly, and it's quickly. When we don't, it's called a cache miss. And then we have to go either the application errors out, or it goes to the database to look for this data. And that's expensive. So we fixed the problem, but now we have this other problem of the cache miss. And what a cache is really like a context window. What is a context window? What is the title of this talk? It comes from the NLP community, and the idea is that it's a range of tokens around a word or given word that allows us to understand the meaning of that word. That's it. We're trying to build history for a given word. So in some ways, a cache is like a context window. So when we say the two sentences, Susanna Clark is an author, she wrote Piranesi. When we say she, we know that we're referring to Susanna because our internal context window keeps that. Machines don't know this. So we've been trying to build context windows into the way that we do machine learning and applications. Like I said, our brains use cache. Our brains use this concept of the context window. So there's this really great book called The Programmer's Brain by Feline Hermans. And she talks about the fact that we have three parts of memory. We have short-term memory, working memory, and long-term memory. And all of those pieces need to work together when we're writing, or more accurately, reading code, because we spend a lot of time reading code. So we have a piece of code. It goes through the filter and then it goes into our short-term memory. And then it also looks up on long-term memory. So the short-term memory is like RAM. It looks up based on what we know from our previous experience. And then it combines all of that in working memory, which is like a cache. And that's how we can read programs. So what happened in December 2022, at least for me I know, and for a lot of my friends who work in machine learning even, was that basically our internal caches broke. It seemed like ChatGPT came out of nowhere. Nobody had any idea what to do with it, and everybody was kind of dumbfounded, even in machine learning. This was kind of like my context window when ChatGPT came out. I had no idea what was happening. But what happens is if we go back, if we start to build context, we can build up to this. Context windows themselves are not new. So, well, we can think of it as a Markov chain. Before you get canceled, disclaimer, LLMs are not Markov chains. A lot of people get angry about this. But what we can think of is that they have similar statistical properties. So hundreds of years ago, a dude called Markov, and others before him who built up to this concept, have this idea that you have two states, and you can think of these as characters or letters or anything, and you have the probability of transition between those states. So the first of this was the first order Markov chain, where the probability of transition from E to A is 0.7, and E to E itself is 0.3, and you get this from past data that you pull. So you know that the next generated letter or token or what have you, these are the two probabilities. This is a very simple way of understanding the relationship between two events. It's simple, but people have been using it for a very long time. And in fact, in this book, Practice of Programming, from Kernighan and Pike, who wrote a lot of the Unix kernel, which the Linux kernel that Alan Ullman then tried to install is based off of, have this practice problem for you to practice programming. This book is really great, by the way. And they say, we're going to implement Markov chains. So this is not new. And even yours truly has been implementing Markov chains. Don't look at this code. It's very bad. It's from 2015, when I was a new engineer. I basically implemented this program to create Hacker News headlines, which is essentially kind of what ChatGPT does. So you can see the results are iffy, but it's like a baby LLM. So the Markov chain gives you the first token of context in our sentence. And now we're starting to build our context window. We have this foundational structure that we know this has happened before. Next stage. Turns out that one-state transitions are not really good, especially when you're dealing with a lot of texts. And Google and other companies started working with n-grams. They released this in 2006. And the idea is that you can now look at more, and however many, 1, 2, 3, et cetera. So then you start to build statistical models of not just the next token, but 2 or 3 or 4 tokens surrounding it, so that then you get to the point where your context window is the entire sentence. Did a lot of stuff with this. So now we have another tool in our toolbox to understand how we can perform text analysis. Then, that wasn't enough, because they were doing a lot of text processing. So in 2013, between this, by the way, there's a bunch of other statistical methods that I won't get into for the sake of time. But word2vec was the next really, really big one. And this was one of the first neural network approaches to understanding context windows. Google released it in 2013. And this is a neural network. So what it does is it takes the inputs and it creates a set of embeddings, or contextual representations of words, instead of manually calculating them one by one. And then it gives some sort of output probability, kind of like Markov chains, that the words are related to each other. So there's 2 different architectures. There's SIBO and skipgrams. The way SIBO works is it holds out a single word from a sentence, and then based on the embeddings it learns, it says, how likely do you think it is that that word is likely to be in the sentence? And then it'll give you an output set of probabilities, much like a Markov chain. So in our case, what we would do is we'd hold out wrote, blank, create a statistical model for it, and then say she wrote Piranesi, which gives us more context. So we're continuing to build context windows. However, it had a bunch of limitations due to its architecture. So then people started looking at other neural network approaches to this. And the next one after this, so fixed embeddings, you can't really change them. If there's a word that's not in the vocabulary, you have to retrain the model again and again. And because the context window in that model is set, it's also limited by the context window. So now we have 3 levels of approach. So now we have Markov chains, the statistical language modeling that I skipped over, LDA and LSA. And now we're at neural nets. So none of this is new. We're just building up and learning our history. Then we get to recurrent neural networks. This was able to do variable length sequences because it had a look-back window. But it was computationally very, very expensive to perform. So then Google, again, invented the transformer. It didn't invent the transformer. It put together a bunch of different concepts in a paper where it said, how do we deal with the fact that this cannot perform computation in an efficient way? And what it came up with was this concept of attention. And attention, there's a lot of explainers different of it. Basically, it keeps track of all the words in your given text and how they map to different representations and creates weights of them. So now we're transformers, and GPT, which is a type of transformer, does the same thing. What is attention in reality? It's just a hash map which is what a cache is, but with probabilistic vibes, which is what Markov chains also do. It's all the same. When we build to these concepts, we're increasing our own context window for what we learn and for what we know how to do. And in fact, if we go back to our cache situation, Redis, which I'm going to talk about in a second, its acronyms are Remote Dictionary Server. So a cache is a hash map, is a context window. And it turns out that context windows are also important with ChatGPT. Because in March 20th, there was a memory leak. I don't know if you remember this, but you could see other people's chat titles and maybe some of their contexts. And here's what happened. So the way the inference server for ChatGPT works is you have this chat history, you have the web client, and then you have Redis, which keeps this chat history. And the way it works is through Python async IO, through the Redis Py client library. And it creates basically two queues, one where it pushes stuff onto the queue, and one where it pops stuff onto the queue to return it. And then when it actually needs to perform inference, it goes to the model Python server that's running on Kubernetes on like the 7,000 nodes, or whatever they have this cluster. But what happened was they pushed a library update, which broke the push operation. And when the push operation breaks, the connection is drained, and the chat titles are no longer connected in push and pop, so you can get someone else's chat titles. And that's essentially what happened on March 20th, which they fixed right away. But it turns out that all this stuff, even though it seems crazy, it's all interconnected, and it works together. So even if you use ChatGPT, you still need to know hash maps. This says I have 5 minutes, but I should have more, right? Yes. OK, cool. Thanks. There's no way I'm going to get through everything in 5 minutes. There's a lot more context. OK. So what context windows do is they give us the ability to be really confident engineers. They allow us to understand engineering. They allow us to understand the hype of LLMs, which is really just foundational concepts building and building on top of each other. And they allow us to evaluate the hype of not only LLMs, but the ecosystem itself. So they're really important, and we need to continue building them. So now we get to the second part, which is naming things. So we talked about cache invalidation, which is really hash maps, which is really context windows. Now we're going to talk about why naming things is important. And if you don't have this first part of hash maps and context windows, you cannot get to the second part. So we've all had this thing where we try to pick a name for a variable. It's like, do we call it X? Do we call it notebook version 5000? Should it be a cache? Is it a data store? Is it a vector? Is it a list? Why is this so hard? And there's a really cool book that came out recently called Naming Things by Tom Benner. And the reason that naming things is hard is because we need to know, one, exactly what the thing does, the name for a thing, and that the name will be reused in the code base. So given all of that, there's a lot of pressure to come up with really good names, because we need the context window of the historical context of the name, business context, the context of our code base, and the context of the computer language that we're working with. So let's say, for example, you're building a semantic search engine, hypothetically, that recommends you books based on vibe. So you have a search query. It goes through a Flask API. It hits Redis. It comes up with books that are similar to the keywords that you entered, and then it returns the results. And let's say that this is based on embeddings, which are context. And then let's say also that we need to return these results to the user. How would you go about naming the process that regenerates the embeddings? Because as you know, in machine learning, we create one model, then we iterate, and it's not good. Then we need to check again. Then we have 4 versions of this model. So let's say you need to re-index these embeddings over and over again. So the problem is to write a modular class that repopulates a cache with embeddings, which are context. What are embeddings? Someone wrote a book about this, TLDR. The rules for naming classes, so when we think about what we want to name it, it needs to be a noun, should be consistent with the rest of our code base, and easy for humans to read. So you could go something like embeddings writer, or data writer, or when you're tired of naming stuff, just vector putter. None of these really work well, so what we can do is we can dig through history. And it turns out that some smart people before, in the early 90s, had written a paper, one of the first recommender systems, called Tapestry. And this was in like 91 or 92. And the idea behind Tapestry was to use collaborative filtering, where you could use other people's actions to determine what kind of stuff you got recommended. And in this case, the stuff was messages from mailing lists in your email. So people, it turned out in 1991, people were already flooded with messages. So there's no hope for us today. And so the way the system worked was it created a list of collaborative actions based on what your coworkers or other people, this was developed at Xerox, had been interested in. So if you dig through the paper, it turns out there's this thing in the architecture, there's this thing called an indexer. So it reads documents from email, newswires, et cetera, and the indexer parses those documents into a set of index fields that can be referenced in queries. There it is. We already know that indexer as a concept exists as early as the 1990s. And so what we can do is we can name our class the indexer. OK. So I've talked at length about why it's important to have the historical context and keep that historical context. How do we do that? How do we build this for ourselves? There's a couple of different ways. One is to become a binary tree. So a tree is a structure in computer science which you can traverse efficiently. You can traverse it either breadth first, which is across the width of the tree, or depth first, go really deep in one thing. You can do both of these. And that's what I suggest that we should become. We should go breadth first, and then we should go depth first and find out what we need to know. So first of all, read broadly. You don't have to read everything, but just a little bit of things to get enough idea. So this is what I started out. This is kind of like a picture of my stack of books, like 2-3 years ago. And the important thing is that they should also, some of this should also be books. I think we forget a lot of times that we can read stuff in books for computer science and data stuff. And the further back you read, like for example, the book from 1999, Art of Programming, the more stable that stuff is, like it won't change every couple years. So I had this stack, and I was overwhelmed by how much I had to read. But the second part of it is, so my husband Dan, who is also a software developer, he's tired of me complaining about this all the time. He said, look, if you read part of this stack, some of it is going to relate to other concepts that you understand, right? So if you read about binary trees, then you know about graphs, then you can know about hash maps. All of these concepts relate to each other. So if you read one book, you have to read less of the second book and less and less. So you can go broad, but then that ends up not having to be as broad. And then second is read deeply. So especially if you're interested in like the LLM stuff or just in general, read papers. So I was reading a paper a couple weeks ago on GPT training data, and it turns out that they use Spark and Spark's native algorithm, which is not something you really associate with GPT, right? It's sexy in the cloud, it's new. They're just using Spark to clean it. They're just like the rest of us. And the second thing is read code that you use a lot deeply. So the code that you read at work, any code that you might come across. So I was curious, like when you do Git, I misspell Git commands a lot. I was curious how the autocorrect works. And it turns out you can just, they will just let you go to the Git repo and look at the code. And you can just see that it's Levenshtein distance. So stuff like that really helps you understand that nothing that we're working with is really magical or mystical. It all builds on top of each other. 2, get out of your head, talk to other humans. That's why we're here, right? We're in an in-person conference. It's great. There's no social media here. It doesn't exist. Just talk to other people. Talk about their work problems. Ask them what they're working on. It might be that they're working on some of the same stuff that you are. And that's what helps us build context windows as well. So in Piranesi, the book, Piranesi himself is observing flocks of birds, because this is one of the things he does. And he says that the wisdom of birds, not in the individual, but in the flock, in the congregation. And outside of books, talking to people who are doing living, breathing data science is very, very good. Then, build from first principles. So later in the book, Ellen Ullman talks about being close to the code. So this was in the early 90s still, but I think the same concept still applies. There's the idea of being close to the machine. And what that means is being close to the source of whatever it is happening. So when an engineer refers to low-level code, it's good. When we talk about low-level stuff in real life, it's bad, but our low-level code, it's good, because it means we're closer to understanding the fundamentals of whatever it is going on. Low is better. So what are some ways you can become close to the machine? So I really like this from Andrej Karpathy, where he, in like the world of vector databases and vector stores, he basically keeps his vectors in an NP array. I do not recommend this in production, but if you really want to understand how vector retrieval works, this is a fantastic way. You can build it, you can look at it, you can introspect it, and then you can understand how some of these larger systems are making the decisions they do. That's being close to the machine, because you're abstracted away from the cloud, abstracted away from vendors, APIs, you're close to what is actually going on underneath. Sebastian Raschke, who also has a fantastic resource on machine learning, he says that he implements some of his own algorithms from scratch. Now, you don't always need to do that, but if you want to understand something, whatever algorithm means for you, it could be a machine learning algorithm, it could be building a cache, it could be moving data, it could be a database. Whatever that is, try building out from scratch to see if it gives you intuition for how to do that. And then think about how it relates to the higher level concepts you're working with. And finally, build with joy. So this is from Mythical Man Month by Frederick Brooks. And he says that the programmer, like the poet, works only slightly removed from pure thought stuff. He or she builds castles in the air, creating by exertion of the imagination. And that's really cool, that you can take something from your memory, from the programmer's brain, and put it down, and build it, and have it be out there. The most important part of this is to actually ship something. So Mitchell Hashimoto, who founded HashiCorp, has also a really cool blog. He wrote that when he broke his tasks into chunks by seeing forward progress and then shipped it, that was good for him. And in data land, that can be really hard, especially when your deliverable is a piece of data or context. But the more we allow ourselves to ship and execute, the more exciting it becomes for us to explore these things as well. So, TLDR, hash maps, caches, context windows are all the same. Keep building them. The more you build them, the more you're going to be empowered, especially in the fast-moving world of data. And that's it. Thank you so much.